Let me see. Hopefully they'll pick up from the one before, right? Right, so the question was, the load where Hooks was exceeded, I was like 54, right? Next. What was the stress in the wire when it began to deviate from Hooks law? Right? How we find stress again? How you find stress? Right? So do me a favor, find the stress. Stress is equal to force over area. Find the stress, please. Right? What was the force? What was the force? 54. How you find area? Pi r squared. It'll be a wire, right? So it'll be circular. So it will be pi by r squared. What's the diameter again? Diameter was 1 millimeter. So that will be 0.5 by hold on, let's handwrite it in about. Let's get a pen to try. Right, we'll call that please. Yeah. Yeah, diameter is 1 divided by 2, that's 0.5. Tension, right, Trips? Yeah, that's right.
No, it was me. It was.
And it was you can create the kilojoule man. Sylvester Bush, who called it in a
Yeah, BCT needs to, it's serious, it's a serious condition. You don't have this?
No, I don't want to know.
I black and cap in basketball. He can play basketball.
Come on again, please. How much will I get? We all get the answers. Shazana, how much will I get? 6.88 by 10 to 3. 19. Ten to the what? Again, 7 by 10 to the 7 pascals, right? Anybody got that one, 6.18 by 10 to the 7 pascals? Wait, standard. Anybody got that one, Katrina? Dylan, what you all got? I tell you how much you got. Why I tell you, how many points you have to do? Oh yeah, without question, I tell you. Oh, they got it, right? Wait, okay, no, online there. Online, you're here, right? -7, 9, it should be +7. Remember, it's 54 divided by, right? Oh, look at that now? Look at that. Positive 7, right? Okay, all right, nice. Next part. Jacob, next part. Question said they want the strain. What strain has the wire undergone at that point? Right? How you find strain? So you said that strain is equal to extension over original length. What was the extension at that point? And make it right. It was 0.75. So 0.75 divided by all the original length. So the answer is what? 3 point, 0 point.
Because the other guy coming up.
No, they'll cancel. They both in millimeters and they'll cancel. The unit will cancel.
There's 2 meters.
Oh, I don't know that. It was 2 meters. Okay, sorry. So the top will be 0.075 by 10 to the minus. How much is that? 3.75 by
3.75 times 10 to the minus.
minus. Right, so that's the SI unit. Sorry, I told you 2 was in millimeter. You all okay with that? Let me see what one line, if one line paying attention. Bob, you there? You working it out? Ask your Ali. Okay with that? Marquis, last part. Well, that's the value for young for train, right?
I didn't know that really.
But some pay attention.
I tried.
Find Young's modulus. Remember how we find Young's modulus?
Stress over strain.
Right? And what was the stress value?
Minute.
6.88 by 10 to the 7. What was the?
The strain?
Yeah, what was the strain?
Yeah.
You just try to make it wait for you. And now right now, how much you got? 1.83 by 10 to the power of
11. I get it. It's positive, not negative.
and the SI unit is what?
You have to let that use.
Pascal.
Pascal.
Because that's not right.
Yeah.
All right. Are you okay with that? So that is finding Young's modulus using 1 point. What I want you to do for me now is find the gradient and use it. Okay. So let's see how close this to the actual value. No, that's an L. That's original length. That's original length. Go ahead.
What?
Right. When you found the gradient, what I got? When you found the gradient, what I got? Right. When you all found the gradient, what we got? Tell me the values again, please. Point 0.7554 and right. All right. By 10 to the minus 3, how much you got? 7.1, thank you. By 10 to the power of 5. Nice. And then we can find Young's modulus by finding the gradient. 7.1 by 10 to the 5 by the length you all said was 2 meters, right? And the area is pi r squared. R was 1 by 10 to the minus 3 over 2, and then you square. How much is that? 1.8 by 10 to the 11. Right? And our value was what? What was our value from the using 1 point alone? Same thing? Same thing. Okay? Right? So we're able to see that it could work, right? We're able to see that it both could work. Everybody okay with that? Hello, Antonia. All right, so basically all we did so far that was new was introduce these 3 quantities: stress, strain, Young's modulus. We looked at the graphical approach of how to find Young's modulus, and we also did a calculation to see how to find Young's modulus. Right, let's go again. Right, let's continue with the small notes. Let's continue with the small notes, right? Head of elastic and plastic deformation. Head of elastic and plastic deformation, right? Let's see the power of 4. Right, so you're supposed to get the same value here, though, right? What you all got here? 10 to the 4, 10 to the 5. 10 to the 4? Hi, Chan, what you got? Well, all it is just work it out. Why is get error when I do? All right, yeah, it's 4. All right. So let's go back to the little notes there. Head of elastic and plastic deformation. Elastic and plastic deformation. Catch this graph here, please. Catch that graph there of stress versus strain. Yeah. Right. Consider the following stress strain curve. Consider the following stress strain curve. Consider the following stress strain curve for a typical metal in the form of a wire. For a typical metal in the form of a wire. Right, so let's go with the labeling. O to A. O to A is a straight line. O to A is a straight line through the origin. O to A is a straight line through the origin. Stress is proportional to strain. Stress is proportional to strain. Therefore, force is proportional to extension. Therefore, force is proportional to extension. And the wire obeys Hooke's law. And the wire obeys Hooke's law. And the wire obeys Hooke's law. And at level 2. And the wire obeys Hooke's law. Full stop. A is the limit of proportionality. A is the limit of proportionality. And A to B is the elastic limit. And A to B is the elastic limit. A to B is the elastic limit. Full stop. If the elastic limit, A to B is the elastic limit.
So say that again.
Which one? A to B is the elastic limit. A to B is the elastic limit. Full stop. If the elastic limit is exceeded, if the elastic limit is exceeded, if the elastic limit is exceeded, the material will no longer be if the elastic limit is exceeded, the material will no longer regain its original shape. Now, say the wrong thing. It will no longer regain its original shape. It will no longer regain its original shape. It will no longer regain its original shape when the force is removed. When the force is removed. Remove. When you remove the force from the wire. Right? O to B, O to B, O to B is called plastic deformation. Sorry, elastic. Sorry. O to B, as in boy, right? O to B, the wire undergoes elastic deformation. Sylvester, you have all of this?
Yes.
Yeah, how much last thing? No, that last one. O to B, the wire undergoes elastic deformation. Next, full stop, next line. B is the yield point. B, capital P, is the yield point. That's right here, right? So from here to here is elastic deformation. Anything beyond here is where plastic deformation will happen. So P is called the yield point, beyond which plastic deformation occurs. Beyond which plastic deformation occurs. Plastic deformation occurs. Right? Put in brackets, the strain is now permanent. Put in brackets, the strain is now permanent. The point C, right? Look up here. The point C is the maximum stress. Right? This graph should go down a little more. Huh? Right? The point C is the maximum stress. And is referred to as breaking stress. And is referred to as breaking stress. Now, the point C is the maximum stress. And is referred to as breaking stress. And last thing, at point D, what do you think happens at point D? Marquis, what do you think happens at part D? As in those?
No more.
No more what?
Strain. Stress.
At the point D, the wire breaks. Yeah. At the point D, the wire breaks.
Yeah, well, if it can't get any more stress and strain, you had a break.
So you didn't say that.
I was trying to let you do it.
All right, nice. So that's the first part. The last thing that we have to do theory-wise is something called strain energy, right? Let me color right out one time. Yeah, and then we'll do some calculations next. Strain energy, last thing. Strain, huh? And next time. Strain energy, last new quantity. Marquis, just do my favor, you can just summarize the graph there for me.
Alright, so
O to A is what?
what the A? Hold on. What the A is a straight line through the origin. Okay.
Summarize it, please.
Stress is proportional
Make it
to
easy.
strain. Stress and strain proportional.
All right, let me change question. O to P is what? What type of deformation?
What the B?
Yeah, what type of deformation?
Elastic. It undergoes elastic deformation.
And P to C.
Yeah, I know it's C.
P to C is what? What type of
Breaking
deformation?
stress. Breaking stress.
B to C, what type of deformation is that? Plastic,
Plastic.
right? What happens between A and B?
What?
A and B. That's the elastic limit, right? And what is called the point A? What is called the point A there?
The limit of proportionality.
All right, nice.
That's smart difference.
All right, we'll say that. We'll hold up. Last thing. Last thing is strain energy. Strain energy, right? Consider a wire, last thing. Last note for today, right? Right, remember all of this not in the handout again, right? Say other right. Last thing. Strain energy. Strain energy. Consider. Right. Consider a wire whose extension is small. Yeah. Consider a wire whose extension is small when a force F is applied. When a force F is applied. When a force F is applied. If the extension is increased, if the extension is increased, if the extension is increased, if the extension is increased by a small amount, if the extension is increased by a small amount, such that the force can be considered constant, such that the force can be considered constant, right? So we're looking at this, right? We're looking at there's a change in extension, a real small amount. I just joined it last so you can see what I'm talking about. Let's call that delta x, such that the force that caused this constant. Right? So underneath that, work done is equal to work done. Work done. How you find work done again? Work done is what? Force by distance. So in this case, it's delta x, right? So therefore, the work done is equal to F by delta x. The work done is what we call the strain energy, right? So the strain energy is the area of that shaded region, right? You'll see that? If I multiply F by the distance, here, it's like a rectangle, right? Sylvester. If you multiply the length, right? I'm trying to find the area of this region here, right? If I multiply F by this small change in extension here, I'll get the area of this region. And that corresponds to the work done. Yeah, at the height and the width. Yeah, that integration of it too, but I'm not showing that version. So therefore, strain energy is the area of the shaded region in a force extension graph. Right? Remember, work done is strain energy, right? So this small area here is force by change in distance, and that small area is also strain energy. Right? And last part, note that if we use integration, we could also show that. We could also show that strain energy is equal to 1/2 kx squared. Right? This is by integration, but I don't want to show you that now, right? So strain energy is equal to 1/2 kx squared. All right, so that is your strain energy. You have 3 graphs. To give it that one time, so we're not write that next week.
I see, so.
What means time? We are real time. All right. Just 3 small graphs are to give it.
Yeah, right.
All right. So we'll look at those 3 graphs next day, and we will do some past papers on this alone, right? All right. Brian, to my paper now. Send my WhatsApp, please. So I can add you to the groups, right? 7230529. All right, good. This is the last thing in module 3 that we have to finish. Right? Brianna, send my WhatsApp, please.